Right now, adversaries are scraping and, well, hoarding terabytes of heavily encrypted data.
Yeah, highly classified stuff too.
Exactly. And they are doing it with incredible patience, just vacuuming up secure communications, financial records, decentralized ledgers.
Just sitting on mountains of ciphertext.
Right. And why? Because they know a mathematical lockpick is currently being built, one that will pop those files open like a cheap suitcase.
It's a terrifying thought, honestly.
It really is. Welcome to this deep dive. Our mission today is to explore an incredibly dense but frankly urgent excerpt from a paper titled Post-Quantum Resilience in Distributed Ledger Cryptography.
And we're looking at this specific text because it targets anyone heavily invested in the digital asset space.
Right. And it delivers a stark warning. Okay, let's unpack this. The core premise of this text is that the permanent security of blockchains, the foundational trust model we've all built these ecosystems upon, it's actually a cryptographic illusion.
That phrase, cryptographic illusion, I mean, that is designed to be a wake-up call for you listening.
Oh, absolutely.
Our goal today is to dissect exactly how the source material dismantles this illusion of safety. We're going to look under the hood at the mechanics of why our current cryptographic standards are failing.
And what this means for the long-term viability of digital assets.
Precisely. And most importantly, the specific architectural shifts the author's demand we make before a systemic crisis hits.
Because they don't frame this as some theoretical debate for the next decade, do they?
No, not at all. It's an immediate structural fire alarm.
Well, I want to start by looking at the specific phrasing the authors used to describe the threat, because it actually caught my eye for a technical reason.
Oh, the hashing bit.
Yeah. The text explicitly states they are stress testing current blockchain hashing against the looming threat of Shor's algorithm. Now, we need to clarify something for the tech-savvy listener right out of the gate.
Right, because blockchains use hashing algorithms like SHA-256 to chain blocks together.
Exactly. But Shor's algorithm isn't typically the weapon used against hashing. Grover's algorithm is.
Yeah, that's a key distinction.
Shor's algorithm is famously what breaks asymmetric cryptography, specifically the elliptic curve digital signature algorithm, or ECDSA, which is what actually protects the private keys and the wallets.
Right.
So is the text conflating the two, or are they using hashing colloquially to represent the entire cryptographic architecture of the ledger?
That is a crucial distinction, and it's the latter. The authors are using the term broadly to encompass the entire cryptographic apparatus of current distributed ledgers.
Okay, got it.
But the existential vulnerability they're spotlighting via Shor's algorithm is aimed squarely at the digital signatures protecting the assets.
Because Grover's algorithm might just weaken a hash function, right? We could just double the key length to maintain security.
Exactly. But Shor's algorithm completely obliterates the underlying math of our public key infrastructure. It doesn't just weaken the elliptic curve cryptography, it fundamentally solves the discrete logarithm problem.
The very problem that makes those wallets secure in the first place.
You got it.
Let's get into the mechanics of how it does that, because the original text relies heavily on establishing Shor's as a looming threat. But we really need to understand the physics of the threat to understand the author's urgency.
Yeah, we often hear metaphors about quantum computers just being super fast standard computers.
Which completely misses the reality of the mechanism.
It really does.
I mean, think of current blockchain hashing as this impenetrable glass vault that we've trusted for years.
Right. I like that visual.
So if the text describes Shor's algorithm as a looming threat, is it essentially a specialized, high-pitched sonic frequency specifically designed to shatter that exact type of glass?
That's a great way to put it. And what's fascinating here is that the authors do not treat Shor's algorithm as a theoretical possibility.
They don't.
No, they treat it as a concrete, approaching reality, one that demands immediate stress testing of the current systems we mistakenly believe to be permanently secure.
Right, because if I have a classical computer trying to crack a wallet's private key, it essentially has to guess and check, right? It's brute force.
Exactly. Classical encryption relies on the sheer computational exhaustion of classical computers.
Yeah.
If you try to reverse engineer a public key back into a private key, the classical computer has to test possibilities sequentially.
Which would take millions of years.
Right. But a quantum computer running Shor's algorithm bypasses the guessing game entirely by changing the rules of the physics involved.
By using quantum superposition and interference.
Precisely. It doesn't test answers one by one. It loads all possible answers into a quantum state simultaneously.
So it maps the entire cryptographic problem into a massive wave function.
Yes. Shor's algorithm transforms the problem of finding a private key into a problem of finding the period, or the repeating pattern, within a massive mathematical sequence.
Wow.
Once the problem is structured as a wave function, the algorithm uses a quantum Fourier transform. All the incorrect answers destructively interfere with each other.
So they cancel each other out, like overlapping ripples in a pond just going flat.
Exactly. Meanwhile, the correct answer constructively interferes, amplifying its signal.
So when the quantum state collapses upon measurement,
The only thing left standing is the exact mathematical period that reveals the private key. It finds that resonant frequency of the math and shatters it instantly.
shatters the glass ball.
Exactly.
I have to challenge the premise here, though. The text treats this as an absolute, immediate crisis-demanding action today.
It does.
But the tech industry has been predicting the arrival of quantum computers for decades. It's always, 10 years away.
Right, the old joke.
Yeah. So why should we accept the author's premise that this is a looming threat requiring active stress testing right now rather than just more academic posturing? Are we actually on the brink of this?
Well, the authors are operating on the reality of recent breakthroughs in quantum error correction. For a long time, the physical qubits inside quantum computers were too unstable. They were too prone to environmental noise to run a sustained sequence like Shor's algorithm.
But that's changing.
Yes. The literature driving this urgency reflects a shift from purely theoretical physics to applied engineering. Adversaries aren't waiting for a perfect, commercially available quantum desktop.
Right, they're building specialized tools.
State-sponsored groups are heavily funding highly specialized quantum circuits designed to do nothing else but execute Shor's algorithm against specific elliptic curves.
So the text insists on stress testing now because of the lead time.
Exactly. The time it takes to transition a globally distributed ledger to new cryptographic standards is mathematically longer than the estimated time we have left before a relevant quantum computer comes online.
Which brings us to a phrase in the text that carries immense, terrifying weight: the inevitable decryption event.
Oh yeah, that phrase.
The authors state that this looming capability will render traditional distributed ledgers transparent and fundamentally insecure for long-term storage.
It's a bold claim.
Let's dissect the word transparent. It's such a chilling choice of words for cryptography. We usually think of blockchains as immutable, meaning nobody can alter the history.
Right, that's the whole selling point.
But the authors are pointing out that immutability is actually a massive liability when it comes to privacy in a post-quantum world.
If we connect this to the bigger picture, the source is making a profound point about the vector of time.
How so?
Well, a blockchain records everything permanently. Every encrypted payload, every zero-knowledge proof relying on vulnerable math, every supposedly anonymous transaction.
So if you encrypt a file and store it on a traditional distributed ledger today, you are burying a digital time capsule in a public square.
Exactly.
And the adversaries are already digging them up. Going back to my opening point, this is the harvest now, decrypt later strategy.
Yes, the adversaries don't need to break the encryption today.
Because blockchains are public by design, anyone can download the entire historical state of the network. They don't even have to breach a firewall.
They just copy the encrypted ledgers into their massive data centers and wait.
Wait for the decryption event. Let me put an analogy on this to make the mechanics clear.
Sure.
Imagine you wrote all your most valuable corporate secrets or your digital identity parameters in a sophisticated invisible ink and left the notebook on a park bench.
Okay.
You feel secure because nobody walking by can read it. But harvest now, decrypt later, means someone is quietly photocopying every single blank page of that notebook.
Right.
And the inevitable decryption event, the text describes, is the day someone finally patents the specific UV flashlight that reveals the ink.
That's a great analogy.
The moment that flashlight turns on, every photocopy they've hoarded instantly becomes readable text. That's what rendering the ledger transparent means. But let me push back on the text here.
Go ahead.
By specifying long-term storage, is the author implying that even data safely stored away right now is essentially a ticking time bomb just waiting for this decryption event?
Yes. That captures the retroactive nature of the threat perfectly. And the source text is uncompromising on this front.
So it's not just future data.
No. The phrase inevitable decryption event signals that relying on current elliptic curve cryptography for anything meant to be kept secure for the next 10, 20, or 50 years is an architectural failure.
Because the decryption event will happen.
Time is actively working against the existing infrastructure. It's not a matter of if, but when.
Okay, so knowing that this event is inevitable and knowing that adversaries are already hoarding the ciphertext, how does the source propose we actually defend our digital assets right now?
The text outlines a very specific methodology. It talks about auditing specific post-quantum signatures and replacing vulnerable private keys with lattice-based alternatives to insulate digital assets.
Here's where it gets really interesting for me, because we are moving away from diagnosing the vulnerability of prime factorization and elliptic curves and moving into the actual mechanics of a post-quantum defense.
The actual solutions.
Right. It's like taking a standard deadbolt, the vulnerable private key, and swapping it out for a complex, multidimensional maze that traps the looming threat before it can reach the vault.
That's exactly what it is.
So what exactly is a lattice-based alternative, and mechanically, why does it survive the quantum wave function we talked about earlier? And how does the text's pairing of auditing and replacing act as an active insulation strategy?
This raises an important question about the structural differences in the mathematics. We established that Shor's algorithm destroys current cryptography by finding the underlying periodicity, right?
The repeating pattern in the math.
Exactly. Lattice-based cryptography survives because it abandons that type of mathematical structure entirely. There's no periodicity for the quantum wave function to amplify.
So it starves the algorithm of the very pattern it needs to function.
Correct. To understand how a lattice works mechanically, imagine a grid of dots, like a pegboard.
Okay, I'm picturing it.
In 2 dimensions, it's very easy to navigate.
Yeah.
If I give you a specific coordinate on that board, you can easily find the peg closest to it.
Right. Simple enough.
But lattice-based cryptography doesn't operate in 2 dimensions. It operates in hundreds or even thousands of dimensions.
Thousands of dimensions?
Yeah. The fundamental cryptographic puzzle is known as the shortest vector problem, or the closest vector problem.
Let me visualize this. Instead of asking the computer to factor a massive number, we are essentially dropping the computer into a 10,000-dimensional mathematical space.
Basically, yeah.
We give it an arbitrary point in that space, and we ask it to find the absolute closest intersection on the lattice grid.
Yes. And the trick to the encryption relies on something called basis vectors.
Okay.
When you generate your private and public keys in this system, you are generating 2 different ways to describe the exact same multidimensional maze. Your private key is a good basis.
What makes it good?
It consists of short orthogonal vectors that allow you to navigate the 10,000-dimensional space, quickly and easily find the closest point. It's like having a perfect straight-line map of the maze.
Ah, I see. But the public key, the one the adversary sees, is the bad basis.
Exactly. The public key describes the exact same lattice, but uses incredibly long, highly skewed, convoluted vectors.
So for an adversary trying to find that closest point using the bad basis, the computational complexity just explodes.
And here's the crucial part. It explodes for classical computers and for quantum computers.
Oh, wow.
Because the lattice lacks any cyclical or periodic structure, Shor's algorithm is useless. A quantum computer gets just as lost in the 10,000-dimensional maze as a classical computer does. It is mathematical structural noise.
That is a brilliant piece of engineering. But the text doesn't just say use lattices. It specifically pairs active verbs, auditing specific signatures, and replacing vulnerable keys to insulate the assets.
Yeah, the wording is very deliberate.
This implies a heavy operational burden on the user and the network developers. We aren't just waiting for a software patch that magically updates the blockchain in the background, are we?
No. And that is a critical takeaway from the source.
Right.
You cannot passive-aggressively upgrade a blockchain's underlying cryptography.
Right.
The authors use the word auditing because organizations and users must proactively comb through their smart contracts, their multi-signature wallets, and their institutional custody solutions to identify every single reliance on ECDSA.
And then what?
The word replacing means actively generating new lattice-based private keys and physically migrating the digital assets from the old vulnerable wallet addresses to the newly generated quantum-secure addresses.
And doing it entirely on-chain, which costs gas, takes time, and requires immense coordination.
Exactly. It's a massive undertaking.
The text's use of the word insulate really drives the timeline home. You insulate a house before the blizzard hits. If you wait until the snow is blowing through the living room, the insulation is useless.
Great point.
So the text is demanding this massive systemic migration of assets to lattice-based alternatives right now, while the old cryptography is still technically intact, to create a protective barrier against the coming shockwave.
The transition itself is the most high-stakes infrastructure upgrade in the history of decentralized technology.
Because if you don't do it,
Because the moment the inevitable decryption event occurs, any asset still sitting in a wallet protected by classical cryptography can and will be signed away by an adversary.
and the network won't know the difference.
Not at all. The adversary will use the quantum-derived private key to broadcast a perfectly valid transaction, draining the asset. The math won't break. It will perform exactly as designed, just in the hands of the attacker.
So what does this all mean? Let's bring this all together for you listening.
Let's do it.
We started with the realization that the digital ledgers we've poured trillions of dollars into are resting on a foundational vulnerability. The ultimate takeaway from the text we explore today is that the cryptographic illusion of permanent security must be abandoned immediately. Shor's algorithm is not a distant sci-fi concept. It is a mechanical inevitability that uses quantum interference to instantly unravel the public key infrastructure protecting our digital assets.
And the response demanded by the literature is total architectural migration.
Right. Passive hope is not a strategy. The text demands that we transition to post-quantum resilience by actively auditing our current systems and replacing those vulnerable cryptographic standards with lattice-based alternatives.
Those 10,000-dimensional mathematical mazes that inherently neutralize the quantum threat.
Exactly. We have to do the heavy lifting of insulating our digital assets now, migrating them to secure structures before the decryption event arrives.
And as you think about the logistics of insulating those future assets, I want to leave you with a final thought to mull over, building directly on the author's dire warnings about long-term storage.
Okay, what is it?
Let's assume the best-case scenario. Let's accept their premise and assume we successfully do the work. We upgrade the networks. We successfully migrate and insulate all our digital assets into lattice-based wallets starting today, protecting all future transactions.
That would be the dream.
The text still warns that this inevitable decryption event will render traditional ledgers mathematically transparent.
Meaning the UV flashlight still gets turned on.
Yes. So what happens to the historical data? Every private medical record stored on a supposedly secure chain, every piece of supposedly anonymous metadata, every corporate smart contract ever executed under the old cryptographic regime.
Oh, wow.
It is perfectly preserved, immutable, and fully exposed in the hands of adversaries who harvested it.
So even if we flawlessly protect our financial future using lattices today,
How will society handle the sudden, retroactive exposure of our entire past digital lives when those old ledgers inevitably turn clear as glass?
when that quantum flashlight clicks on, it doesn't just illuminate tomorrow. It fundamentally alters the privacy of yesterday. That retroactive exposure? Well, that is going to stay with me. Thank you for joining us on this deep dive. Keep questioning the illusion.